Hi, my name is Eric. Welcome to my channel. In this video, we are going to explore a new programming language called Mojo and use it to implement the softmax algorithm, which is widely used in neural networks. Mojo piqued my interest primarily due to its potential for high-performance computing in AI and machine learning applications. As a language designed to bridge the gap between research and production, Mojo combines the simplicity and familiarity of Python syntax with the performance capabilities of system programming languages like C and Rust. This unique blend makes Mojo an attractive choice for developing efficient and scalable AI and machine learning models and applications. In this tutorial, we will be using Mojo to implement the softmax algorithm. Softmax is widely used in neural networks for tasks like multi-class classification. Along the way, we will learn about some interesting aspects of the Mojo language, such as how to use the move semantics, how to deep copy data on the heap, and how to use Mojo's built-in benchmark package to benchmark algorithms. So whether you are interested in learning about this new language Mojo, or softmax, or how to optimize your code, this video has something for you. Let's get started. In this first section, we will cover some essential concepts related to softmax, namely, what is softmax? What is safe softmax? And what is the online normalizer calculation for softmax? If you are already familiar with these concepts, feel free to skip ahead to the next section, where we will explore how to implement them in the Mojo language. So what is softmax? The softmax function is actually very important in many neural network architectures, particularly for multi-class classification tasks. It takes a vector of real numbers, which we often call logits, as input, and transform the logits into a probability distribution over all the possible output values. The softmax is defined as this. Given xi, which is the ith logit, the softmax of xi is equal to the e to the xi divided by the sum of exponential of all logits. If we just implement this softmax as it is, there will be some problem. Because the exponential of some value can result in overflow if x is very large, or if x is very small, the exponential can underflow to 0. This will lead to some undefined result. So how can we address this overflow or underflow issue? People come up with this safe softmax algorithm, which is commonly used in machine learning frameworks like PyTorch. The safe softmax is invented to mitigate this overflow or underflow issue by subtracting the maximum value from the input vector before computing the exponentials. It is numerically stable and produces the same output as the standard softmax, without any risks of overflow or underflow. However, nothing comes free. You can see that with the safe softmax, it actually has 3 passes instead of 2 over the input vector. The additional pass comes from calculating the maximum value from the input logits, and there's overhead. To address the computation overhead from the safe softmax, people come up with this brilliant idea of online normalizer calculations for softmax. The paper is written by 2 researchers from NVIDIA. Essentially, the algorithm keeps the maximum value m and normalizer term d as it iterates over the elements of the input array. The final result is the same as the save softmax and also numerically stable. You may notice that this method will incur additional math operations per vector element. Will that be problematic? The algorithm works well on GPU because GPUs have high arithmetic throughput but relatively lower memory bandwidth compared with their computation power. According to the paper, online method accelerates by up to 1.3x on GPU. So a natural question is, will online approach also be effective on CPU? My assumption is that the online normalizer method would yield better performance only on GPU, while on CPU the performance might be worse compared with safe softmax. To test this, I decided to conduct a little experiment with the Mojo language. So here is the development plan. First of all, we will take a look at the existing implementation of the matrix struct from the official Mojo tutorial. It has laid a good foundation, but we will need to make a few tweaks. Next, we will implement the column struct using the matrix struct. The column will be used to represent the logits for the softmax algorithm. For the softmax, it will be implemented as methods of the column struct. Finally, we will benchmark the different softmax implementations to compare their performance. Let's get started. So below is the original matrix struct from the official Mojo tutorial. In the first line, it creates an alias type for the data type flow32. This alias is used throughout the code to represent the data type of the matrix elements. The matrix struct takes two type parameters at compile time, rows and columns, representing the number of rows and columns in the matrix respectively. The struct has a single member variable, data, which is the pointer to a dynamically allocated array of type elements. This is the first constructor for the matrix struct. It allocates memory for the data array using dtype allog and initialize all elements to 0 using memset_0 function. This is the second constructor for matrix struct. It takes a dtype pointer as an argument and assigns this to the data member variable. This constructor is useful when you want to create a matrix instance from an existing array of data. Rand is a static method. It creates a new matrix instance with random values. The rest of the methods are for getting or setting element values in the matrix. In the existing implementation, there are a few things that is inconvenient. First of all, user needs to explicitly release the resources allocated on the heap. These three lines, adata.free, bdata.free, cdata.free, is like getting back to the C programming and asks and requires the end user to manually manage the memory. In addition to this issue, we cannot initialize the matrix from another matrix. It lacks in the copy constructor. And we cannot initialize the matrix by moving the data from another matrix. So it lacks in the move constructor. Let's address these issues one by one. First of all, let's try to be RAII, implement the DEL dunder method. And then let's also implement the copy init and move init dunder methods. For the destructor method, the implementation is quite straightforward. We just call the data-free method inside the function body. For the copy init, in addition to the self, we need to take another parameter for the matrix where we want to copy the data from. And then we allocate the data on the heap. And then we use the mem copy function to copy the data from the existing matrix to the self matrix. As for the move constructor, it takes another parameter of the existing. Note that the existing needs to be owned, which means that the lifetime of existing ends after the move init is called. And in the implementation, we just assign the data pointer from the existing matrix to the self matrix. And there is a very important note here. The destructor of the existing method is actually disabled in this move constructor. So that means we don't need to worry about this same resource, which is the data pointer, is released twice. It will only be released once when the destructor of the self is called. Let's run some little test. Here I create M0, which is a matrix of size 1 by 1 and randomized. Now I try to assign M0 to M1, which is going to trigger the copy constructor. Now try to print the first element of M0 and first element of M1 and see if they are equal. Okay, they are equal. That means that we successfully copy the data from M0 to M1. Next, I'm trying to test the move constructor. And it seems that I found a bug with running this module code in the IPython notebook. Here I have the same set of the code in a file, and I try to run it from the command line. Everything just runs fine. But if I run the same code in the IPython notebook, I get some error. I might need to report the bug to the module team, but let's just move on. Next, let's implement the column struct. The column is essentially a matrix of n by 1. So it only has one column, but many rows. It means we can probably take advantage of the existing matrix implementation. However, in the current stage, Mojo does not support struct extending another struct. We cannot do something like implementing column by extending it from matrix. That means we need to use composition instead of inheritance. In the implementation, we will also implement the various softmax algorithms as the struct methods, and also implement the equal to assist us comparing two columns in the unit test. So here is the implementation of the column struct. First, I create an alias, col, which is equivalent to a matrix of only one column. The NELT stands for the number of elements. In the constructors, we simply call the constructor of the matrix to initialize the elements. We also have the same static method to create a randomized column. Then it comes to implementation of the softmax algorithm. Clearly, you can see there are three for loops, which basically has three passes over the elements. In the first pass, we try to get the maximum value among all the elements. And in the second pass, we try to calculate the exponential of each element minus the max. And in the third pass, we calculate the probability of the logit. Down below is the implementation is an online normalizer method to calculate softmax. Compared with the safe softmax, the biggest difference is that we only have two for loops, which means that we only have two passes over the elements. In the first pass, we iterate each element and try to update our maximum value and the denormalizer. And in the second pass, we calculate the corresponding probability. Finally, we implement the equal downer method. We iterate each element and calculate the difference between the self and the other element. And we compare the absolute value to a threshold. If it is bigger, then we return false. Otherwise, we return true after iterating all the elements. Let's do a little unit test to verify that our implementation of the softmax algorithms is correct. First, I create a logits variable, which is a randomized column of 10 elements. I print out the first 4 logits and then call the softmax function to calculate the probabilities. Then I print out the probability of the first 4 logits. It is expected that the larger the logit is, the higher the probability is. I also calculate the softmax using the online approach. It is expected that the sum of all the probabilities should be equal to 1. I also compare the probability calculated from safe softmax with the probability calculated from the online method. Here is the result. By printing out the logits and their probabilities, we can see that the larger the logit is, the higher the probability is, and their sum is also equal to 1. The probability calculated from 2 different methods are equal to each other. So this basically verifies that our implementation of the safe softmax and online softmax is correct. After verifying the correctness, let's benchmark the performance of different implementation. There's a pitfall here. Sometimes the compiler is too smart, and it tries to avoid certain computation if it sees that a certain variable is not used, and that would affect our benchmark result. And to avoid that, we need to use the keep function to give a hint to the compiler so that it will not optimize away certain calculation. So here is an example. Without a keep, you can see the calculation is lightning fast, which is too fast to believe. In this benchmark, I create a column of about 10 million logits, and then I try to benchmark its calculation time using the native and online and also native unrolled methods. Here is the result. The average time to calculate softmax of so many logits is only 1.7 e to the minus 14 millisecond, which is just too good to be true. The naive unrolled, it seems to give a reasonable results, but the online normalization also gives a unbelievably quick result. That makes me think maybe the compiler is optimizing away some key calculation. Here, I'm trying to use the keep. By keep the probabilities calculated from various softmax algorithms. And now, the result seems much more reasonable. I'm benchmarking these algorithms on my desktop, which only has a CPU. And the result shows that online normalization method is actually worse than the naive algorithm on a CPU. And my hypothesis is that on a CPU, the calculation is not memory bounded, but computation bounded. Because the online normalization introduced 2 more math operations, so that's why it gets slower. But how can I prove or disprove this hypothesis? Probably I need more profiling. In the future, Mojo will support compiling to GPU, and I think it's a good time to revisit this benchmark. So basically, this concludes my video. I'm also new to Mojo language and implement this benchmark code by following the official tutorial and the online documentation. So if there's anything that is misleading or confusing or simply wrong, please leave a message to me and I would correct them. And because Mojo is still in the development mode and iterating very fast, Some of the existing methods could be wrong in the future. Overall, I think Mojo is a very promising language, and I plan to do more study on it. And if you like to hear some topics from me, please leave a comment. Thank you very much.